and you had to multiply these two matrices. You're writing the matrix class, so the behavior that goes with it you have to do. What would you do?
Right, another loop. Multiply.
You write a method and call it multiply. Right? That's what you do. That's what you have to do. So you have something like m3 equals m1 dot multiply m2. Makes sense, right? You know this. One of the things you learn early on when you're programming in Java, can you compare strings using the double equals? Well, why not? Because it compares their addresses. Right, well, Java doesn't have operator overloading. C++, is that legal? Yes. You don't have to use dot equals. There is no dot equals. Pointless. Why would you have dot equals? You can do this. Okay. Well, why does this work? Because it's overloaded, and it compares the two actual strings. So this is what's meant by operator overloading. So the matrices here, we can do M1 times M2, but we have to redefine what times means in that context. So we actually write a function that multiplies two matrices, but we name it, that's the name of our function. An interesting concept, yes? A new concept. Well, it exists a little bit in Java. The only place it really exists is concatenation of operators. You can take two strings in Java and you can put the plus in between. Can I say S1 plus S2 when S1 and 2 are strings? Can I do that in Java? And what does it do? It doesn't add them. It concatenates them, puts them together. Right? That's an operator that is overloaded. It's the only one I'm aware of in Java. But here we can redefine operators and have them do what we want. Well, one tries always to make sure that we have done this in a way that makes sense and also covered all the cases. But sometimes essential behaviors are lacking. So you have to be aware that this is not the same thing as a native behavior defined. So here when we have a string on one side and an array of characters on the other, there is a function written that actually copies this thing from one to the other. So that's the overloaded operator piece. Similarly with vectors. With vectors, suppose I have vector B. I said be careful, make sure you use pushback to insert things in the tail end of the vector. If you tack them on the end, you're not going to have any problems. But what if I do this? It's the square brackets that cause the problem. This is an overloaded operator. And the coding for the overloaded operator for the square brackets does not test to see whether or not the container is big enough. It doesn't check. It just does it. So what it does is the address of this vector plus 100 times the size of the elements go there. So if they're integers, it's b plus 400, go there and write it 2. And if it's out of bounds, out of the range of the vector, so be it. This can cause all kinds of problems. Now they could have written the code for these square brackets to test the capacity, and if it needed to be bigger, resize it, but they didn't. They didn't. Therefore, although this might seem reasonable, in fact is an incredibly risky thing to do. So you should do these only for read-only and only if you know they're in range. So back to the topic at hand. Some strings functions for C-style strings that are extremely useful. All right. String copy. String copy. So this is copied from the source to the destination. An assignment statement won't do. Why won't a simple assignment statement work? Why wouldn't a simple assignment statement work? Yeah.
Because you just don't have two character pointers pointing to the same string.
Yeah, it doesn't copy the string, it makes you an extra pointer to the one existing string. If you need to copy a string, i.e. have two of them, just copying the pointer won't do it. Does everybody follow me? You have two pointers pointing to the single one string. That's no good. So if you need a copy, then you need the string copy function. That will make a copy of it. You also have to make sure that the destination is big enough to receive it. If it isn't, you risk a crash. Okay? And then string compare. Compares the two strings and returns an integer. It returns a negative if the first string is less than the second string, a 0 if they're equal, and a positive number if the first one is greater than the second one. Greater than, less than means dictionary order. Dictionary order. Notice the return value too is an integer. There isn't a bool or Boolean type in C. So anything that's not 0 is true. String length.
For string compare, is it positive if S1 is
Greater than S2.
S1?
Yes, if the first one would come after, the first one would come after the second one. Z is greater than A. C comes later in the dictionary. String cat. Destination. And the source. Again, it falls on you to make sure that the destination is big enough. Also, it not only changes the destination, but it returns this. So you have to return that. Not so much. Yeah. So this returns the tokens. It busts it up. This is a primitive function, but it's nevertheless useful. Alright, let's see here. There are also some character functions that only operate on characters. Okay. Well, a character is a string that you have dereferenced or used this way. That's a character. Also, these guys, it's an array of characters, so you've got the index to indicate it.
So is, in order for the delimiter,
I'm sorry?
for the string organizer, is the delimiter potentially another string?
No, it's a character.
We have a character pointer.
Yeah, it can be more than one. Yes, it's a character pointer. It returns a character array as well.
So is it this?
Right. So you need to. I suggest you guys look up the documentation on it to see how it does. But it busts them into tokens based on the delimiter. This is not the best way to do it. This is not the best way to do it. I will give you that. Can you use that to make it work? Probably. But I wouldn't go there. However, these functions you will need to use. And they are handy. So at some point you will want to do these. So these operate on an argument, a single character, which can be a single character in a character array, i.e. a C string or a C++ string. So this looks weird. IS is AL none. Is AL none. And that is it an alphanumeric? A through Z, 0 through 9. So both letters and numbers. And of course it takes a character. Is alpha? Is it a letter? Is control character? Is digit? 0 through 9. So I put character here, but actually it's not. A character is really an integer. I mean, it's a number. Is space. So it's a space character.
What's the one above is the
Is control, CNTRL. It's a control character. So this obviously isn't all of them. Or you can use these to test things to see. Is it a space or isn't it? Digit. Yes.
So control characters are like return?
Yes. The first 20 ASCII characters are control characters. The first 20 are I said 20. In hex it is. The first non-control characters hex 20, which is the space, and that's actually decimal 32. So 0 through 31 are control characters, ASCII characters. Questions? Okay. So I want you guys to look at the string class, and I don't want to tell you how to do it. Again, I want you to solve the problem. But I think if you can use string methods in class string, you will find this job easy. There are methods in the class string that you can use to make this process simple. Look at it and see. Can you loop through it and use these functions? You can. They're going to cut your grade if you do. No, as long as you have it correct and it works correct. But actually parsing things, parsing a line and separating it into tokens is not trivial or easy. The original string tokenizer in Java has had bugs in it for years. And there's certain types of strings that will fail to parse correctly. They've known about it, and since everybody knows what it does, changing it now will cause problems. But it's actually quite difficult to do. What makes this even manageable at all is the fact that there are rules that govern the form that this file, your source code, can take. And it's predicated on predictability that if something fails, then it's wrong, and it needs to match these rules. But a general string tokenizer that works under all circumstances with any kind of text is enormously difficult to write. So use the rules you've been given in terms of parsing your tokens to make your life easier. I mean, you know how many there are, maximum number. You know that there are white space between things. And if you have a single quote that you open, you have to find the closing single quote. But my advice is don't look at anything in between them. You can have something that, a token that looks like this, a message, pc.v, hello world. Of course, this is one token. So if you find an open quote, you just keep going to the end. But this language, there are no double quote marks, only single quotes. So just keep going till you find the close quote and don't even look at it. Questions? Okay. I want to talk about makefiles for a minute. Makefiles. You're going to have to write one. I've given you a sample, and you can use that as your starting point. But if you go over the simple rules that govern this, it will be helpful, I think. Now, makefiles can be enormously complicated, but we don't have to go there. This is a case where knowing a few simple rules will give you the ability to write makefiles for most projects. So, okay, to start out with, you can comment things out if you need to with the pound sign. Then it's a good idea to use variables, or they're actually constants here. CC equals G++. So we define this symbol CC. Now we're going to say, okay, that's our C++ compiler. So that if we need to use or transfer the code to a different kind of machine that doesn't have G++, then it's pretty simple to change it to a different compiler. So you specify the compiler and then the flags. This is the most common. CC flags equals. And then put the string that you're going to use. -G. This allows you to use the debugger. This will put debugging symbols into your object files, which you can then inspect. I'll show you how to do that as we go forward. You can use the GDB, GDX. There are different debuggers installed that you can use to inspect objects. Optimize the code. Capital O, and then the degree of optimization. Doing anything more than 3 is a waste of time. 2 or 3 is a good number to use. Basically what this says to the compiler is go ahead and knock yourself out, see how you can optimize this code. You can do this in Java as well. I don't know if you're aware of that. But when you do it, you do the Java C or Java or whatever you call it, minus capital O with no number, and that causes the Java compiler to optimize. So it takes longer to compile, but gives you more efficient code. There are a lot of techniques that are used, and when we get to the section on compilers later this semester, we will talk about optimization techniques that compilers use.
What's the difference between a 1, 2, or 3?
Well, that's the degree of optimization, right? So you can actually look in the documentation. It will say if you pick level 1, then it will use this, this, and this. And if you pick 2, then it will add this and this and this. And if you do 3, it will also give you this. So there are different techniques. There's probably between 40 and 50 optimization techniques that can be used by others. Really? So this determines how aggressive you want the compiler to be in finding optimizations. You'd think it'd be the default, but it takes longer to compile something with these optimizations. You guys have any sense at all of what these are? Let me do a quick example here, and then we'll return to this. I'm sorry to digress, but I think you guys are interested in this. So let's just do a real simple example. So this is a simple for loop, and you're going to store in the array 1 through 100. Right? So you start out I is 0, so you store I plus 1 in the first slot, right? Okay, so you put 1 through 100 in an array of size 100. Okay, so the compiler will remove the loop. So this is a waste of time. Why is it a waste of time? What has to happen inside this for loop? How many statements get executed after you pass in the loop? Well, there's the initialization step that happens outside the loop. This happens first. It's just a one-off thing. Every for loop has an initialization. It's just one thing, so we can ignore it. So when we enter the for loop, the first thing it does is to check to see if we're done yet. So there's a comparison with I and 100. So it checks. Is I less than 100? If it is not, we're done. If it is, we keep going. So there's a test and a branch condition at the very top to see if we're done. Then there is the assignment. Okay, that's easy. That's one step. So run 2. Now what? I plus plus. Go back to the top of the loop. So 400 statements in the best case to run this loop. 400 statements. Well, could I do this instead? Could I? Would that be fewer statements? 100 versus 400. It would be faster. Yes. It would take a quarter of the time in the worst case. Branching, by the way, costs you something too. So when you jump back up, that costs you something. So this is much more efficient. So this would probably run 5 or 6 times faster than this. All right, so if you ask for optimization, the compiler looks and says, can I get rid of this for loop? Well, that depends on a couple of things. One is, are these values known? The keys off this index variable. Stopping condition is known. Do I have enough information I can get rid of this loop? Well, you have to look at it. You can come up with other types of loops that may be more difficult to remove, not as easy to remove. So this is just one simple example of how, if you compile the code as written, you have one result, but if you optimize it, you have a faster execution. Questions about that? Okay. So, O3, more than O3, doesn't seem to be all warning. Then there's some other ones that I've asked you to do. Yes.
Can you assume that if you did O3, it would not break anything? Let's see.
Oh, it won't break anything. Well, that's not a bad question. There are types of code where if you do these optimizations, it may break something. And usually what happens is the developer that's writing the code knows that if the structure is changed in any way, it will have a side effect. And so there are switches that you can include in your code that tells the compiler, don't tamper with this. This section do not touch. Compile it just as it is. So warnings all, and there are a couple of others. There's a casting check that I asked you to use. Pointer check. So you put the switches in. There's several hundred of these. There are all kinds of options. If you know exactly which CPU this is going to be used on, you can specify exactly that CPU. And the compiler will use the instruction set for that exact CPU to give you better code, rather than a certain family of processor. Do you want 64-bit, 32-bit code? So you can specify these things. This, however, I would consider the bare minimum. But use the flags that I've specified for yourself. Okay, now you have targets, we'll call them dependencies and commands. That's the general format. And these go from the bottom up. The last command executed is the first one. So they go on a stack, you'll process that way. So the last one you want is the name of your executable. So we might have something like driver. And then you have to specify the resources required for the driver. So we might have something like driver.cpp, file, parser, whatever files are required or referred to, referenced inside the driver. What's required to make this? And then we have the command. C flags. So the brackets are just a way to refer to them. But substitution is what it is. Minus O driver. Let's see. This executable. So further down here, you might have file parser dot O. That's what you want to build. What do you need to build this? You need file parser dot H. You need file parser dot CC. You need file parser parse exception. H, and then you have CC flags, minus C, which is compiled but don't create an executable. This will make a .o file. File parser .cc. That will make the object file but not link it. And then the top one does the linkage. So you have rule, or you have target, resources, command. Command on the next slide. Very important, the space in here has to be a tab character. You can't use spaces. If you set up your editor to insert spaces instead of tabs, which is what I always do, it won't work. So you have to use actual tab characters there. Questions? Yes?
So the CC and CC flags, they substitute for the values?
This gives you direct literal substitution. So here, $ brackets here, it does G++ minus G minus O3 minus W all minus O regulars. So it's direct literal substitution is what it is. They're like macros. It does the substitution. This allows you to easily make files for more than one platform. It's fairly common. So if you look at, say, an open source C++ project, you'll see something like this. Makefile.com. Makefile.button. Makefile.solaris. Makefile.suse. The different various operating systems. So then the common file has the, you can think of that as the main or overarching piece. But then the specialized bits go in the SUSE, Solaris, Ubuntu files. Yes?
So you have just the CC, G++, flags in the file?
It depends. These can be enormously complicated. What we also have is conditional compilations. You may have if tests and things like that. But this is the usage. And then this is a capital M here. It's a capital M, not a lowercase m. So then you need to type make, if there's a single make file, which is what you will need to do. You just type make lowercase m. And it looks for make file, capital M. On some systems it works if it's a lowercase m and make file, but that's not how it's done. Go ahead and capitalize. Or you can say make minus f make file dot SUSE. You have SUSE. So make using that particular custom make file. So you can use the makefile.com to find things that apply to every system, and then specialized bits in here. So almost all of these will have at the top of them include the makefile.com to start with and then specialized pieces. Questions? Yes?
So what's the difference between .cc and .cc?
Well, it depends on who you ask. That is, there isn't one right answer. The convention I use, which I want you to use in this class, is that a CPP file is only for the C++ file that has been used. So you have driver.cpp. But if there's no main method, then it's a CC. So file parser.cc, not CPP. You do not want to put a main method in the file parser. That would make sense. Other questions? Alright. It may seem strange and confusing, but it's nevertheless true. You can put code in an H. However, if you do that, it should be as short as possible because it becomes inline if it's in the H file. By that, it's handled differently. It's handled by the macro processor, and the instructions are inserted into the method where it's called. So, as an example of that, I have class stack here, and all of the code is very short. So I could easily go ahead and include it all in the H file. But rather than calling functions, there will be no functions. If I have s.push, it's not a function call. Rather, that function call s.push is removed, and it's placed the actual assignment statement. The body of the method in the H file is inserted. You with me? Rather than jumping to a subroutine, doing something, and coming back, the body of that method is inserted in the source code. So there's no subroutine call. It's faster, but it also makes the code larger. So it's a macro, which is what we're going to be working with this semester. We're writing a macro processor that does exactly this. Okay. So I also want to focus on templates. The syntax is not terrible. Templates allow you to use any type. You've seen these parameterized types in Java. This is somewhat different. So, you have your normal stuff, template standard, so on, and then you have templates. Class. Class. Stack. So T is the type, but it can be anything. Public. Colon. Stack. Now, another thing we have here that you don't in Java is you can set the type values this way. So a person can pass in a value here, but if they don't, they get 100. So it's the default. There, put in the code. Push. What are we pushing? So T is the type. And we'll just do that, please. Right. So we might have, say, part size. We might have top, which is not necessary. We have the part size. So here I have put them both places. I then put in code in the H file, and also put in the CC file just to show you what's possible. And you can do this if and only if with small amounts of code, like this, delete. So this is a destructor. Well, we don't know how big the storage needs to be until runtime. The user says stack 1 million, stack 100. When you write the code, you have no idea. So it's got to be dynamic. Okay, so let's write the implementation. So we have the constructor inside the .cc file here. This one is the .h, stack.h, template, class t, stack, double t, double colon, stack. S for size. Okay, so current size equals 0, top equals -1, storage new of new t So I've done this with new, which means I have to give it back. I'm done with the stack, otherwise I haven't been able to leave. So this is when you need the destructors when you're creating class level variables using new. Okay. Int stack t double colon push constant. So where you have references and then read only, you should always declare them as constant. And item. Is full return 0. And then storage plus equals item. Like so. Okay, so if you do this now, you can use templates for any of these container type classes. And you're not limited. In Java, they have to be objects. You can't use int. You use integer, but not int. C++, no such limitations. Also, the compiler will generate code specifically of the type requested. So if you have 5 different kinds of things in stacks, then you get 5 different kinds of stack code in the object code. So you get exactly the type you need, and there's no runtime to see what it is, figure it out, all those methods. So it's faster. Okay, I see we're out of time. Well, we will continue this discussion.